Hello, so this is video number 2 of section 5.3. Basically in this video we're just going to diagonalize some matrices. So I've got 4 examples attached to this video. Again, I don't want to make this extremely long, so we'll kind of start working through these examples, and then depending on how much time everything takes, we may or may not get to all of them in the video, but whatever we don't get to, I highly recommend looking over the worksheet and trying some of these examples on your own, as I will post all of the solutions. So what are we looking to do when we diagonalize a matrix? So I've got kind of the steps outlined to how to diagonalize a matrix that are given to us by theorem 5 of last video. So if we want to diagonalize a matrix, and we're not already given its eigenvalues and eigenvectors and such, if we're just given the matrix and asked, is this matrix diagonalizable? Here's what you do. First, you find all the eigenvalues. So we've seen how to do that. Next, you find all possible linearly independent eigenvectors. And so we'll see some examples, certainly where step 2 is a little more involved than it might initially seem. So remember, of course, each distinct eigenvalue has its own at least one linearly independent eigenvector corresponding to it. And so sometimes this process just amounts to finding one eigenvector for each eigenvalue, but sometimes you do have to find multiple eigenvectors for a single eigenvalue. Finally, this is where theorem 5 kind of kicks in. If there are n linearly independent eigenvectors, v1 through vn, then the matrix is diagonalizable. The matrix P, which is this invertible matrix diagonalizing A, is just the matrix whose columns are the eigenvectors of A. We saw that last video. The matrix D is the diagonal matrix similar to A under this similarity transformation, whose diagonal entries are the eigenvalues of A, and specifically lambda 1 is the eigenvalue whose eigenvector is v1, lambda 2 is the eigenvalue whose eigenvector is v2, and so on. If we do not have n linearly independent eigenvalues, then as theorem 5 told us, A is not diagonalizable. So using these steps, let's diagonalize some matrices. So I figured I'd start off with a 2x2 example. Those tend to be the easiest, and really the process to doing this is the same as you increase dimension. It's just, every time you add sort of an extra row column, it gets longer and longer every time you add a row and a column. So first example, we want to diagonalize A if possible. So we're given the following matrix, 2, 3, 4, 1. So first thing we want to do is find the eigenvalues. And to do this, we want the characteristic polynomial, which remember is the determinant of A minus lambda sub I. So this would be 2 minus lambda, 3, 4, 1 minus lambda. Which is equal to lambda squared minus 3 lambda plus 2 minus 12 lambda squared minus 3 lambda plus, minus 10. And factoring that, we get this. And so, of course, this step, if you need to factor this polynomial and certainly can't remember a trick, you could always use the quadratic formula as sort of a fail-safe. What's so fun about the quadratic formula, of course, is that it comes with a song. What's interesting, so I had always thought the quadratic formula song was set to the tune of Pop Goes the Weasel. So x equals negative b plus or minus the square root, and so on and so forth. But I heard, actually, I think last year, I was talking to students who said that they had learned it to a different song, and I can't remember what song that was. All right, so we've got 2 eigenvalues of A, lambda 1 equals 5 and lambda 2 equals negative 2. And we know, actually, again, from what we talked about last video, these are the only eigenvalues of A, right? This is the foolproof way of finding all the eigenvalues of A. Since A is a 2 by 2 matrix, we actually also know that there are at most 2 of them. So next we want to find the eigenvectors. So we'll start with the eigenvector for lambda 1 equals 1. Maybe I'll sort of... And so actually, right off the bat, I can tell you, and we're going to state this, I think, in the next video as a official theorem, but right off the bat, you should be able to tell that this matrix is diagonalizable, right? Because, and as I'll set this problem up, I'll talk about it, that because so you should be able to tell that this matrix is diagonalizable because it has 2 distinct eigenvalues, right? Each of these eigenvalues is going to have its own linearly independent eigenvector. And so, in fact, right, like, because of that, this matrix will have 2 linearly independent eigenvectors, as we'll soon see. And so actually just knowing that there are as many eigenvalues, or as many distinct eigenvalues, as there are columns and rows in the matrix is enough to tell you immediately that the matrix is diagonalizable. But we'll still show it by finding all of the eigenvectors and such. So we want to do 4/3 row 1 plus row 2. And then negative 1/3 row 1. And so remember, this means that the following, well, so if we're looking at the homogeneous equation corresponding to this matrix, we get x1 minus x2 is equal to 0, or x1 is equal to x2. And so if we write out this solution to the homogeneous equation in parametric vector form, right, we get 1 times s is equal to 0, 0. And so this means that the vector v1 equals 1, 1 is an eigenvector for A corresponding to lambda 1 equals 5. So again, that's how you do that. Maybe in the interest of time, considering this video is, we're going to be doing a few examples, I will just give you the next eigenvector and let you, I'll leave it as an exercise to do this amount of work. Before I do that, I'm going to plug my computer in as it's running out of batteries. All right, sorry about that. Didn't want to lose what I'd already recorded there. So yeah, we found one eigenvector, right, corresponding to lambda 1 equals 5. So I'm going to leave this up, and I'll at least give you the setup for the next eigenvector, and then I'll maybe skip over the row reducing just a little bit in the interest of time. So next, we would want to find an eigenvector for lambda 2 equals negative 2. And so this would mean we'd want to row reduce the matrix A minus negative 2 times I, which is equal to the 2 by 2 matrix, 4, 3, 4, 3. And so doing that, you would wind up with a row-reduced echelon matrix of the following. So 1, 3/4, 0, 0. And this would correspond to the homogeneous system x1 is equal to negative 3/4 x2. And so remember that would mean the parametric vector form for this would be negative 3 over 4, 1 times this free variable t is equal to the 0 vector. So looking at this, I haven't used this trick yet, but I will often kind of quote this trick. So notice, again, this would be like just negative 3/4 1 would be an eigenvector corresponding to negative 2. But remember, every linearly independent, every scalar multiple of this vector is also an eigenvector. So in this case, I'm going to let t equals 4 because this will get rid of all the fractions. And in fact, I know that negative 3, 4, where I'm letting t equals 4, is an eigenvector of a corresponding to lambda 2 equals negative 2. And that's again because any scalar multiple of this vector is also an eigenvector. And so I'm just allowed to use any scalar multiple of this vector. And so I'm just going to multiply by 4 to clear all the fractions out, just because it's easier. All right, so we found now 2 linearly independent eigenvectors and their eigenvalues. And so we're almost done. So given this fact here, we know that A is equal to P times D times P inverse, where P, remember, is the matrix whose columns are given by the ordered eigenvectors. So the first column is V1, the second column is V2. Then D is the diagonal matrix whose ordered diagonal entries, that's the word, that's the, when your entries are matrices, they're called entries. Right, whose ordered diagonal entries fall in the same order as the columns of P. So again, the order corresponds to the eigenvectors here. And so this would actually be enough to show, okay, A is diagonalizable. How do we check this, though? So you should always be thinking, okay, you want to verify that this is true. And don't show this is true, right? So we actually know P is invertible because we know that these two columns have to be, or these two vectors have to be linearly independent. So if you wanted to show this, right, you'd have to calculate P inverse and then do a bunch of multiplication. You should actually show that A times P is equal to P times D. Because this is equivalent to this, because we already know P is invertible. And this is a lot easier to show. And I'll show you quickly why, because it's the same amount of matrix multiplication, but we actually don't have to calculate any inverses. So doing the matrix multiplication dance, I get that this is equal to 5, let's see, 6, 5. All right, everything's looking good so far, negative 8. And then P times D. Well, this one is a little easier to calculate. Sure enough, we get the same thing both times. Since these two things are equal, and we know P has to be invertible because its columns are linearly independent, we know that, in fact, this diagonalization, we checked or verified that this diagonalization is in fact valid. All right, so what I'm going to do, there's one more 2x2 example. I'm going to leave that for you. You're actually going to show that that matrix is not diagonalizable. I want to move on to example 2 on the next page, and we're going to look at a 3x3 matrix. So there's actually one more example of another 3x3 matrix. as well. So I'll do half the examples in the video and then leave half the examples as practice for you at home. So we want to diagonalize, if possible, the 3 by 3 matrix. A is equal to 1, 1, negative 1, 2, 2, negative 2, negative 1, negative 1, 1. And what's nice is that in this problem, the book gave us the eigenvalues, I guess because it figured we had enough work to do without them. But why I wanted to look at this is because A only has 2 eigenvalues. So what I want to do is look at what do we do when a matrix only has 2 eigenvalues, and sort of what does this matrix either being diagonalizable or not being diagonalizable look like. So what we still need to do in order to diagonalize this matrix, since we already know the eigenvalues, is find its eigenvectors. And so I'll start with lambda 1 equals 1, meaning I want to row reduce the matrix A minus 1 times I, which is equal to 0, minus 1 times I. Oops, sorry, I entered the matrix wrong. Apologize for that. This should be 2, 3, 2. So the matrix we're working with is actually that matrix. And then I think I accidentally wrote on the board the matrix we wanted to look at here, which is A minus 1 times I. So the original matrix I wrote on the board was the matrix A minus 1 times I, but I sincerely apologize. The matrix we're looking at is this one, so 2, 2, negative 1, 1, 3, negative 1, negative 1, negative 2, 2. These are still its eigenvalues, and this is the first step here. So looking at these rows, I noticed something a little interesting. All of these rows are pretty much the same, so I can actually do a lot of row reducing in, I guess, 2 steps that I'm turning into 1 step, where I'm going to add negative row 1 to row 2 and row 1 to row 3 to get the following. And this is actually now in reduced row echelon form, so that was nice. So I want to now figure out how to find the eigenvectors associated with this matrix. So x1 is the only non-free variable. And so solving for x1, we get that x1 is equal to negative 2x2 plus x3. And so remember here, because we have more than 2 or more than 1 free variables, the parametric vector form corresponding to this solution will look like this. Where S is a free parameter, just a real number corresponding to whatever value I were to give x2, and T is a free value, or just free parameter, corresponding to the value I'd give x3. But notice that every solution to this homogeneous equation represented by this matrix is a linear combination of these 2 linearly independent vectors. So this means that I have 2 linearly independent eigenvectors for the eigenvalue lambda 1 equals 1. So this is sort of another example of a matrix with, only 2 eigenvalues, but notice one of those eigenvalues actually has 2 distinct linearly independent eigenvectors corresponding to that eigenvalue. All right, so we're still not done finding eigenvectors, however, because now we need to find the eigenvectors for lambda equals 5. So lambda 2 equals 5. If I want to find the eigenvectors for this, I need to row reduce the matrix A minus 5 times I, which is equal to so you could do this and get the same eigenvector you're about to get, but I'm going to sort of introduce yet another trick you can use. So notice if you took the absolute value of all of the terms in the matrix A and summed them up. So remember, we sort of introduced this idea that the vector 1, 1, 1 is an eigenvector of a matrix if the row sum across all of its rows is the same. Look at the absolute value of the row sum of that matrix. So 2 plus 2 plus 1 is 5. 1 plus 3 plus 1 is 5. 1 plus 2 plus 2 is 5. So if we had a vector that could, in a sense, make the signs of all of those entries the same, then we could kind of use a little bit of a trick to make sure it's an eigenvector. So notice this vector, 1, 1, negative 1, when matched up with A, well, each entry in the row, the first two entries are going to stay the same sign. The third entry is going to flip signs. So if I add up all of the entries in the row, then 2 plus 2 plus 1 is 5. 1 plus 3 plus 1 is 5. Negative 1 plus negative 2 plus negative 2 is negative 5. And so this is an eigenvector for lambda 2 is equal to 5. And I'll say look at row sums. And I'm going to put row sums in quotes because it's not exactly row sums. So this is like kind of a trick that you should be very careful using, the trick I just used here. Certainly row reducing the matrix A minus 5I would like always get you the correct answer no matter what. And if you're not absolutely sure of this, I wouldn't do this. I also wouldn't do this if you're thinking maybe there's going to be multiple eigenvectors associated with lambda 2 equals 5. In this case, I know there's not going to be, because at this point I found 3 linearly independent eigenvectors associated with this matrix, which is, I know, the most I'm going to be able to find. So given these 3 eigenvectors, I'm going to let P be the matrix negative 2, 1, 0, 1, 0, 1, 1, 1, negative 1. And so remember then, I have to make D the diagonal matrix whose ordered diagonal entries correspond to the eigenvalues of A in order corresponding to the vectors I put in P. And so it would be like this. And so notice in specific here, the first 2 vectors both correspond to the same eigenvalue of 1. The last vector corresponds to the eigenvalue of 5. And so you could verify that A is equal to P times D times P inverse. And just for the sake of time, remember you would verify this not by checking this, but by checking this. So, like I said, there are 2 more examples of diagonalization on the worksheet, which I will leave for you to look at, but I will post the solutions at a later time.